Hey guys, last time you guys have seen some forces, and today we're going to see some more and how we are actually shoving them on an object. And this is called free body diagram. Alright, so before we start, let's talk about properties of forces. The unit for force is Newton. And why do we have it Newton? Because this famous scientist and mathematician Isaac Newton, so he figured it out, and then that's why we have the unit as Newton. And the way that we abbreviate Newton as capital N, and the symbol for force is capital F. Alright, so we basically had field forces, and that's what you have seen in the previous class. And forces act from a distance. So for those field forces, you do not need a physical contact. So for gravity to pull things, it doesn't need to be attached or like touching to the object. It can actually pull things from a distance. And same idea with this strong nuclear force, electromagnetic force, and weak nuclear forces. You have seen the details, but this is basically just to classify them as field forces. Alright, and we also have some other forces, and we call them contact forces. And what is the difference for a contact force? You need a physical contact to be able to act actually on the object. And what are the common examples of contact forces? Frictional force, tension force, normal force, applied, drag, spring. And you have some more, like buoyant force is one of them as well, or but these are going to be the ones that we're going to be using in most of our cases. So it's important that you know those 6 contact forces. Alright, so what is a free body diagram? So mostly we're going to be abbreviated as FBD. So once you see FBD, that means free body diagram. What is the meaning of it? It is pictorial representation that is showing all of the forces acting on the object. Alright, so this hiker, for example, there are a lot of things going on for this guy. So, and showing all of the forces acting on this guy with the arrows, with the vectors, we basically call it free body diagram. So let's see what we have in this case. You have the pull of the rope from the top, and then something is pulling it down, which is pull of gravity. And then this guy is touching the mountain on this part, so it is basically, he is pushing. Alright, so that's the thing. He is pushing on the mountain, but this is the force that is not acting on him. What is acting on him? Action, reaction. So when he's pushing on the mountain is actually pushing back on him. So basically, push of the cliff is going to be the force on the hiker. So we are not writing the things that the object is applying around, but we are actually talking about the forces acting on our object. And what else do we have? So basically, he is trying to push his foot down, and because of friction, friction is basically resisting the movement of down, so it's basically friction going up as well. So once you put all of those forces together, so this is not the free body diagram, this is showing all of the forces acting on the person. But how do we show free body diagram? Number 1 rule is represent the object with a dot, and then show all of the forces with their labels, all right, with a vector. And as you can see, this says pull of gravity, but this is saying FG. This says push of cliff, but this is basically going to be the normal force. All right, so that's basically what free body diagram is. All right, so how many forces acting on the climber, and what are they? Well, you basically have 4 forces. So what are they? Friction force, tension force, normal force, and gravitational force. Alright, so now let's talk about the details of those forces. Gravitational force. What is gravitational force? It's simply the weight of an object. So how much you weigh is actually a little bit wrong usage, because how much you weigh is your mass, like how much pound times gravity. Alright, so weight of an object is basically calculated with mass times gravity. And gravitational force changes due to gravity of the planet. So you are going to have different Fg. And when are you going to have different Fg? You are going to have different gravitational acceleration. So how do you have different gravitational acceleration? You basically change your planet. Once you change the planet, your gravitational force will change. And what is the direction of gravitational force? It is basically straight downward. All right, because this gravitational force is always towards the center. So in here, actually, if you think about that angry bird, what is the gravitational force acting on him? Towards the center. Alright, so that's what gravitational force. And how do we abbreviate it? It's either Fg, or sometimes we're going to see this as mg. Alright, so both will be okay for gravitational force representation. Alright, so if a mass of a sumo wrestler is 200 kilograms, what is his weight? So normally you might be thinking he weighs 200 kilograms. Actually, that's wrong, because 200 kilograms is the mass of him. But how much he weighs? It's basically calculated with mass times gravity. So gravity will be taken as 10, so 200 times 10. So he actually weighs 2,000 Newton. Alright? So the unit for force is Newton. And weight is in force. Alright, the next one is normal force. This is the one that is confusing the students the most. But the simple version of saying, like, when do we have a normal force? When you have a contact with a surface, you must have a normal force. Alright, because it is action-reaction in between the surfaces. So if you're in contact with any surface, then you're going to have a normal force. And what will be the direction of normal force? It is basically, let's say for this kid, the plane of the surface is like this, then you are going to be 90 degree to the surface. Alright, so that is basically your normal force. Alright, but what about this guy? The sliding guy, the surface is not horizontal, it's diagonal. Then what will be the perpendicular force for this, or perpendicular vector for it? This is going to be the vector, so that is going to be the normal force. Alright, so the direction is away from the surface, and it is perpendicular to the surface. And apparent weight will be basically equal, like normal force. Well, we might not talk about that later on, but that's an extra information. So what will be the amount of normal force? Normal force is basically the sum of all forces acting towards the surface. Alright, so for this case, gravity is the only force that is acting on the surface. Then normal force is equal to gravitational force. But for this guy, gravity is acting straight down, but it is basically with an angle. So normal force is going to be equal to the perpendicular vector that is going down to surface. Alright, that's going to be a little bit confusing, but main idea is when you have a surface, you must have a normal force. Alright, tension. What is tension force? It's transmitted through a string, rope, or wire, or anything like that. So tension force is directed along the wire. So if you look at those cases, the tension doesn't have a certain direction. Whatever the direction, whatever the orientation of the string, that's where the tension is. It is going to be along the string, so whatever the angle on the string is, that's basically how your tension shown. And as you can see, gravity is always straight down for all cases, but depending on the angle of the string, your direction of tension might change. And on the same string, you're going to have the same force. So for example, for this guy, let's say they are pulling this with 100 newtons and then they are pulling it with 100 newtons. What is the tension on the string? It is 100 newtons. All right, so because they are trying to pull with 100 newtons and then tension is basically keeping it away from moving. So that means tension on the string over here is 100 newtons. And same idea for this group. They're trying to pull it this direction and tension keeps it away from movement. So tension is also 100 newtons. So you don't add them up. Whatever the tension at any point at a string, it is going to be the same on the same string. And how do we show them? FT, or sometimes you're going to see this as capital T. All right, friction force. What is friction force? It's resistance that is opposing the motion. All right, and what is the direction of force? Friction force, opposite of direction of movement. All right, and how do we show friction force? With F sub F. All right, so this friction force is going to be a little bit different because it is going to have another equation to calculate it. So friction force is going to be calculated with normal force times mu. What is mu? It is basically a Greek letter, mu. All right, it is coefficient of friction. So what is coefficient of friction? Basically, it is a number that is in between any two surfaces in contact. And that coefficient of friction will depend on those two surfaces in contact. All right, so for example, ice is going to have really small coefficient of friction, so it's not going to resist the movement a lot. All right, what is the other type of force that we might have? It's drag force. It is, you can say that's the friction of air or any fluid. So drag force is also known as air resistance. It is, again, like I said, is a frictional force that acts upon objects as they travel through air or fluid. It's going to be a better definition. And the force of air resistance always opposes the motion of the object. So same idea as friction, is going to oppose the movement. And the force will be frequently ignored. Okay, the friction force, air resistance or drag force, they are going to be ignored most of the time. So when do you know that there is drag force or air resistance? They need to state that. All right, if it's not stated, then you just assume that there is no air resistance. And terminal velocity is the velocity at the moment the air resistance is equal to the gravitational force. All right, that terminal velocity is a little bit confusing concept. So gravity pulls things down, right? But air resistance depends on the velocity of the object, which means as you go faster and faster, then this drag force is going to be more and more. So what does that mean? After a while, your gravitational force is going to be equal to that air resistance. And when force that is going down equal to force going up, what does that mean? You have no net force acting on it. So that means there is no acceleration. If there is no acceleration, what's the meaning of that? That means there is no change in velocity. So that is the term. The terminal velocity is that velocity when you reach to the point where your air resistance equal to your gravitational force. So after that point, you are not able to speed up anymore. You're just basically falling with a constant velocity. All All right. So, for example, for parachute, once you have the parachute deployed, the air resistance is too much. So what's going to happen? It is going to reach to the terminal velocity so fast, then you're not going to speed up after a while, and your velocity is going to be really small enough that is not going to hurt you when you land. Alright, and once object reaches to that velocity, it falls down with a constant velocity. Alright, that's that terminal velocity. Alright, and this is basically the summary of it. So if you would like to have, if you have an applied force, it's basically shown with FA. What is the direction? In the direction of applied. What is the reason? When do you say that there's an applied force? There must be an outside force by a person. Is there any extra equation for it? No. Drag force, it's basically opposite of movement. What is the reason for drag force? You need to be moving in the air or fluid. You have an extra equation for drag force. As you can see, it's depending on velocity. As velocity goes more up, then your drag force is increasing, but you don't need to know that. You're not going to have any question about it. So friction force is also, again, opposite of movement. What do you need to say that there is a friction on the surface? Uh, by words, if you see a rough surface, then you know that there's a friction. Or sometimes you will see that like an object is standing on a like slanted surface, but it's not moving. Then you can also uh, say that there is a friction. But most of the time you basically look for a rough surface, and if it's not stated, then you basically assume that there is no friction in the surface. And there's an extra equation to calculate friction force. It is Fn, which is normal force, times mu, which is coefficient of friction. So gravity, or gravitational force, what is the direction? It's always straight down. When do you say that there's a gravitational force? You basically need a mass, like huge mass. So we generally state that if there's a planet in a system, then you basically have that gravitational force. And how do we calculate gravitational force? Mass of the object times gravity, or gravitational acceleration. All right, normal force, what is the direction? Perpendicular to the surface. When do you have a normal force? When you have a contact with a surface. What is the equation? There's an extra equation, but it is the sum of all forces towards the object. So spring force, when it is basically just like tension, it's going to be along the spring. When do you have a spring force? If there's a spring in the system. And again, we're going to see this later on, but there's an extra equation for spring force. It's K, force constant, times X, distance stretched or compressed. And tension, it is going to be along the wire. And when do you say that there is a tension? If there's a wire, string, or a rope in a system, then we basically know that there is a tension in the system. So that's how we basically know, or that's how we classify forces, and that's how we analyze their directions and how they look. All right. Normally that was a PowerPoint, so you didn't need to see those, but there was no way to separate it, so I'm just going to go with the answers on it. So object slides down on a smooth surface. So if it says smooth, then you know that there is no friction. And draw the free body diagram of the object and label each force. So what do we start with? You basically start on the object first, and then you are going to draw the free body diagram separately. And this dot is going to represent the object in this case. So you always start with the forces that we talked in here and see what you have. So gravity, if like otherwise stated, you always know that there's a gravity in the system, and it's always straight down. So you always start with that. And then next, what do we look at? You basically have a surface and there's a contact with the surface. Then what do you require? You basically require a normal force. And what is the direction of normal force? It is perpendicular to the surface and away from the surface. So this is my surface and this is basically perpendicular line. So that's why this Fn is going to be my normal force. So this guy right here is my free body diagram. So you basically have a point, a dot representing the object, and showing all of the forces with the labels with vectors. All right, vectors, so they must have a direction representing the movement direction. All right, so that's what a free body diagram is. All right, let's have one more example. So object is motionless. So what are you going to look at? You basically, again, start with gravity, because gravity always pulls things down. And then you have two string in the system. Then how are you going to, like, if you have string in a system, then you are going to need a tension in the system. And what will be the direction of the tension? It's going to be along the wire or a string. So in this case, your free body diagram is going to look like this. You have the object, gravity pulls it down, two strings are acting on that object diagonal, and that's basically your free body diagram. So there is no surface in contact, so there is no normal force, there is no friction, there is no spring in the system, so there is no spring force, there's no applied force. So you basically write down all forces and then check which ones are in the system, and then just write them down. Alright, so that's basically what free body diagram is and how we actually use this free body diagram.